once we had the counting numbers, so we had 1, and then we had 1 and 2, and then we had 1 and 2 and 3 and more than 3, and then we had 1, 2, 3, and then somebody came along and said, well, I could have 4, and then I could have 5, and then I could add one more and have 6, and continue like that forever. Once we had that, then we had the set of natural numbers. And I'm writing, I call it a squiggly bracket, but it's just a brace, like you see on your keyboard. The natural numbers are the counting numbers. They start at 1, and then you just count 2, 3, 4, 5, and so on. Those ... things that I just wrote there mean and so on. And then when we're talking about sets, we close the squiggly bracket. They're like a grouping symbol. And I'm also going to put on here counting numbers. Let me spell it right. Counting numbers. So if somebody tells you to start counting, you'd start at 1, 2, 3, 4, 5, and you'd keep going. Okay? So like the year 2014, that is a counting number because you could count. Just like we've been through all those years, eventually we got to 2014. 2014 is a counting number. So therefore it's a natural number. The number we haven't talked about yet, that's a natural number, not a natural number, but we naturally want to talk about it now that we know what it is. We didn't have this number for a very long time. What number don't you see up here? 0. We actually, as humans, we didn't have a concept of 0 for a very long time. 0 and the natural numbers makes the set of whole numbers. So I'm going to do a squiggly bracket here, and now I'm going to start at 0. 1, 2, 3, and so on. So the only difference between the whole numbers and the natural numbers is the inclusion of the number 0. Okay? All right, what numbers do you not see up here now? The negative numbers. 4, 5, 6, 7, 8. This is the ... means it goes on forever. Okay? So we have all the positive counting numbers. We don't have any of the negative, we could say, counting numbers. Okay? So it turns out that once we figured out that we needed some negative numbers, we said we could have all of the natural numbers and their opposites, all of the whole numbers, including 0, and their opposites. As soon as we figured that out, it gave us the set of integers. So I'm going to start, I could go forever in this direction. I'm only going to write up to -3 though. -3, -2, -1, comma, 0, and then just keep going with the whole numbers. 1, 2, 3, and so on. So the integers are all of the whole numbers and their opposites. And we know what opposites means, right? So what's like the opposite of 4? Good. Let me just change the sign. That gets your opposite. So I'm going to write that over here. All of the whole numbers and their opposites. Those are like the friendly numbers that we prefer to work with. So now that we have positive numbers up here and we have negative numbers up here and we also have 0, we can talk about what set of numbers is the positive numbers and what is the negative numbers. So we can write that down a little bit more formally. If I pick a number, any number, then I'm going to call it x. X represents any number. If x is going to be positive, what has to be true mathematically? Yeah, the sign will have a plus on it. But what has to be true mathematically of x? It has to be what? Give me like vocabulary that you know. Starts with a G. There's a symbol associated with it. You usually say something about alligators. Yeah, greater than. Greater than what? Okay, technically a positive number has to be greater than 0. But we are going to include 0, so I'm going to say greater than or equal to 0. Good. Technically 0 is not positive. It's also not negative. It's just 0. But usually when we work with 0, we consider it to be positive. So that's why I'm including it there. And therefore, based on this notation that we see, what could we say the negative numbers must be? Very good. X is less than 0. Not less than or equal to. It can't be equal to because we just included 0 in the positive numbers. So that means 0 can't be a part of the negative numbers. All right, let's talk about rational and irrational, the last two up here. These are the ones that you probably haven't heard too much about. You haven't worked with them very much. Once you learn what they are, though, you'll realize that actually you have worked with them to some extent. The rational numbers, the word rational actually gives away how you remember what a rational number is. Very good, ratio. The word ratio in rational tells you what kind of numbers you're dealing with. What is a ratio? What's a ratio do? Compares two things, right? Or in math, we are comparing two numbers. How do I show comparing two numbers? A fraction, yeah. A rational number is a fraction. So like 3/4. 3/4 is a rational number. I'm going to add to that though. A fraction, or the decimal, that's decimal, stops or repeats forever. It can stop. If the decimal stops, it's a rational number. If the decimal repeats, it's a rational number. Okay? So with the fraction stuff that we were doing last time, that big chart that we made, pick one of the decimals on that page, just randomly. Shout one out. 0.4. 0.4. What fraction does that correspond to? Okay, 2/5. Is 2/5 a rational number? Yes, because you could write it as a fraction. Is 0.4 a rational number? Yes. Why? Because what doesn't repeat? Because the decimal stops. It can either stop or it can repeat. If it does either of those things, then it is a rational number. Okay, give me another one. 0.25. Is 0.25 a rational number? Yes, because what? The decimal stops. Give me another one. Do we have any on there that has a decimal that doesn't stop? Yeah. 0.1 repeating. Is that a rational number? Yes, it is. Why? Because the decimal repeats. Okay? So does the decimal stop on 0.1 repeating? No. But it does repeat. And that means it's a rational number. Incidentally, what fraction goes with 0.1 repeating? 1/9. And 1/9 is a fraction. Okay? So that is a rational number. All numbers, this is important. You might want to write this one down off to the side. I'm not going to write it up here. All numbers that we know of, all real numbers, are either rational or irrational. They have no choice. It's one or the other, never both. So if we have all of our rational numbers here, they're fractions or decimals that stop or decimals that repeat, then the definition for irrational numbers is going to be decimals never stop. And the word and is very important. The and never repeat. Very good. So, irrational numbers. The definition for irrational numbers that we're going to need to know is that the decimals never stop and, at the same time, they never repeat. And I already heard one example, pi. Pi is what? Okay, we call pi 3.14. That's the rounded version. Does that decimal stop? Does that decimal stop? Yes. When you round a decimal, you make it a rational number. But pi itself is not rational. If you look at the top of my board, you'll see pi. Is it just 3.14? No. It's all of these decimal places. And what should I have down here? It should keep going. I can't do that, obviously. There's like trillions of decimal places that we've calculated out to for pi. It never stops. And it never repeats. People have spent their entire careers looking for a pattern in pi to say that pi is actually a rational number. But they've never found one because there isn't one. Pi is irrational. Okay? You can calculate the next number. There's a way to do that mathematically. We can't do that in Algebra 1. By the time you get to calculus, once you've been through geometry, you can use geometry and calculus to come up with a way to calculate the digits of pi. That's one way. There's several other ways that you can do it. But that's the idea, okay? The decimal for pi itself, not the rounded version, pi itself is an irrational number. There are others. The number e, which you will work with, some of you, before you graduate from high school in math classes. The number e is also irrational. We have things that you have worked with. The square root of 2 is irrational. Meaning that if you were to find the square root of 2, you get like 1.414 and then a bunch of other decimal places. The calculator will stop displaying digits eventually, and it will round. But that doesn't mean that the square root of 2 is rational. It is still irrational. The square root of 3 is also irrational. There are no two numbers that multiply, or there's no number that times itself gives you the square root of 3. You get a decimal if you try to take the square root of 3. Every time you get a decimal when you take the square root, it is irrational. Okay? How about the square root of 4? Is the square root of 4 irrational? No, why not? The square root of 4 is 2, and 2 is an integer. It's right here. It's also a whole number. It's right here. It's also a natural number. It's right here. Is it also a rational number? Can I write 2 as a fraction? 2 over 1. Did I write 2 as a fraction? Yeah, okay. There's a little bit more involved with the definition here. It has to be an integer divided by an integer. And that's what we have here. So 2 actually is a rational number. We said that the square root of 4 is not irrational, which means the square root of 4 must be rational, because all numbers fall into either this one or this one. They have no choice, okay? So if you can take the square root of something and get an actual number, then it is a rational number. All right? Square root of 4 doesn't count. How about square root of 5? Irrational. Good. And how about the square root of 8? Can we take the square root of 8? Really? Give me a number that times itself gives you 8. So we got 2 times 2 is 4. And then the next one, 3 times 3 is 9. And we're already past 8. So is there a number times itself that gives you 8? Nope. Therefore, the square root of 8 is irrational. If you take the square root of 8, you get a decimal. 2 point something. Probably like 2.8 or 2.9, right? Okay, so I could do it without a calculator very quickly because in my head, I know how to do that estimating that we've been doing. Right? Okay. So that's your sets of numbers right there. All numbers fall into these categories right here. All real numbers that we're going to be working with in this class fall into maybe one or maybe many of these categories. What was our first set that we talked about? The natural numbers. And then we talked about the whole numbers. The only difference between the natural numbers and the whole numbers was what? 0. All the other numbers are the same, right? So would you say that the natural numbers are a subset of the whole numbers, or would you say that the whole numbers are a subset of the natural numbers? The natural numbers are a subset of the whole numbers because all of the numbers in the natural numbers are also part of the whole numbers. Got it? All right. The next set we have is the integers. Does the integers have more numbers than the whole numbers or less numbers than the whole numbers? Seems like more. Actually, that's kind of a trick question because the answer is they have the same amount of numbers. But in reality, like in this classroom, do we have more numbers with the whole numbers or more numbers with the integers? Seems like the integers, right? Because the whole numbers start at 0 and go this way. The integers have 0 and go this way, but also have -1 and go this way. So is the whole numbers a subset of the integers, or is the integers a subset of the whole numbers? Whole numbers are a subset of the integers, okay? How about rational numbers? A number can be rational, a number is rational if it can be written as a fraction with integers dividing integers, like 2 over 1. But we also have some other fractions, like 3/4, 1/8. Which set has more numbers in it, the integers or the rational numbers? The rational numbers do, because I can take any integer I want and divide it by 1, and that will be a rational number, right? I can divide any integer by any integer I want, and I will get a new rational number, which means that the rational numbers are a huge set, way bigger than the integers, okay? And finally, irrational numbers. Would you say that the rational numbers are a subset of the irrational numbers? You don't think so? Why not? Actually, there's an infinite number of both. Is the rational numbers a subset of the irrational numbers? Think about what they are. What is the set of rational numbers? What is the set of irrational numbers? Can you be in both? What did I say earlier when I said what these are? Can't be in both. So therefore, can they be subsets of each other? No. You're one or the other, not both. So therefore, they are not subsets. Okay? All right, what we're going to do now is put these sets into two different visual charts for you. You can use one or the other. I'm showing both because some people like one over the other, and that's fine. We'll work with the Venn diagram looking one first. All of the numbers that we have, all the numbers that we're going to be working with in this class are what we call real numbers, okay? The real numbers are all going to be fit inside this box right here. So up top, I'm putting real numbers. We do have to say real numbers because there is such a thing as imaginary numbers. You'll learn about those in Algebra 2. Okay, all real numbers that we have are either what? Irrational or rational. Now, if you are an irrational number, that's all you're ever going to be. You have no subsets beneath you. So, from the real numbers, will irrational numbers go in this big box here or in this rectangle off to the side? Rectangle off to the side, good. The irrational numbers are their own thing. If you have an irrational number, there are no other subsets for it. But it is still a real number, and that's the important thing. So if this is irrational, then what goes over here in this big box? Rational. Okay. What is the next biggest subset of the rational numbers? Go ahead. The integers, that's right. So in this big circle here, we put the integers. If you are an integer, therefore, are you a rational number? Yes. If you are a rational number, does that mean that you are an integer? No. Okay? The Venn diagram shows that we could have numbers out here, like 3/4 would live right about here, because it's not an integer. What is the next subset down from integers? The whole numbers. If you are a whole number, are you an integer? Yes. If you are a whole number, are you what's the last subset? We already have integers. We have whole. What's the smallest subset we have? Natural numbers. Okay, so if you are a whole number, does that mean that you are also a natural number? If the natural numbers are a subset of the whole, does that mean if you are a whole that you must be a natural number? No. Okay? Actually, there's only one number that is a whole number but not a natural number, and that number is 0. Okay? So that's how the Venn diagram works. My advice to you is to decide whether you have an irrational number or a rational number, because all numbers are one or the other. And then if you have a rational number, start at the bottom and work your way out. Is it a natural number? Yes. Then it's therefore also whole, integer, rational, and real. Is it a natural number? No. Fine. Is it a whole number? No. Fine. Maybe the number's -3. Is it an integer? Yeah. Then it is also a rational and real number. All right, that's how that works. Now the tree is very similar to the Venn diagram. It just doesn't take up as much space. So at the very top, all of our subsets lead to what major? The real numbers. Thank you. And we said the real numbers get split into rational and irrational. Which one am I probably putting on the left? Rational. The ones that can be made fractions. Irrational basically means they can't be made fractions. The prefix ir on irrational tells me they can't be fractions. Okay, if you're rational, you could be, you might not be, but you could be what? An integer. And if you're an integer, you could be whole. And if you're whole, you could be natural. All right, so on the subset tree here, if you find out that you are a natural number, then you are also everything above it. If you find out that you are an integer, then you are also everything above it. If you find out that you are a rational number, like 3/4, then you are rational and you are also real. If you find out that you are irrational, then you are irrational and you are also real. So therefore, every single problem that you do that asks you to classify numbers will have two answers. You will either be rational or irrational and real. You might also be an integer, whole, or natural if you're rational. All right? So let's see how that works. We have a bunch of practice problems here. Name the set or sets of numbers to which each real number belongs. You're going to have two automatically. Let's take a look at 5/22. Is that a natural number? We're starting at the bottom of that tree. Is it natural? No. Is it whole? No. Is it an integer? So the integers are the nice, easy numbers. There's no decimals, there's no fractions. It's just 1, 2, 3, 4, 5, and they're opposites. -1, -2, -3, -4. That's not that, right? So it's not an integer either. Is this a rational number? Yes. It's written as a fraction. So it's rational, which means it's also real. All right, that's as far as you can go with that one. How about the square root of 81? It is real. We'll get there. Why? That's what? You're probably not wrong. Tell me why. The square root of 81 is 9. And what kind of number is 9? Go all the way to the bottom of the tree. Is it natural? Is it a counting number? Yes. So 9 is natural, which means the square root of 81 is a natural number. If it's natural, it's also what? Whole, which means it's also what? Integer, which means it's also what? Rational. And? So go to the bottom of the tree, and if it fits, it's everything, it's that one and everything above it. If it doesn't fit, move up. How about the square root of 56? Okay, I heard irrational. Why would it be irrational? There's no number that times itself gives you 56. There are two numbers that multiply to give you 56, but that's not what we're doing here. We're not doing 7 times 8. We want the same number multiplied times itself. And that doesn't happen. And since that doesn't happen, that means it is irrational. And since it's irrational, it's also real. All right, one more. -3. What is it? I heard integer. Is it a whole number? Why not? Because it's negative. The whole numbers and the natural numbers do not have negatives in them. So if you see a negative sign, it can't possibly be either of those. But it is an integer, which means it's also what? Okay? Good. Now, your homework is going to have problems like this. You're going to take a quiz pretty soon, not today, that has problems like this. And there's problems like this on your chapter test. So it's kind of important that you understand how to classify these numbers. Make sure you understand this. Don't just give me one answer. Give me the answer and then everything above it. Graphing on a number line. I know we all know how to graph on a number line. We've done this before. But I want to show you how to do this correctly, especially when you have weird stuff like fractions. So what should I probably do if I'm supposed to graph on a number line first? All right, let's draw a number line. Try to make it straighter than I can draw. Now what? What numbers? Where should we start? It seems like, and I know that you've probably been taught that, you should put 0 in the middle. But you don't have to. 0 might not even be a part of your number line. You should actually start on the left. I want to pick the number that I need to have here in order to fit all of my numbers to the right. So what number should I put? I don't want to use the numbers that I'm given though. -3 would work. Is that the smallest number I need to use? I need -1. Okay, -1 will work, so I'm going to put -1 on here. I want the first number that doesn't contain those numbers that I'm trying to graph anymore. So -1 is perfect. Now let's do the same thing on the right. The biggest number I have to have. 2? Is this more than 1? Is this more than 1? What is this? It's actually 2. So I can put 2 on there. All right, now we have -1 and 2. We should probably fill in the rest of the number line with nice numbers, nice integer values. So I'm going to put 0. Undo that. I'm going to put 0 here and then 1 there. Notice now where 0 is. 0 did show up, but is it dead center? No, it doesn't have to be. Start on the left side, and then go to the right side, and then fill in your numbers after that. Did I write a bunch of fractions on my number line? No, I have integers on my number line, okay? Set up a good scale. You're going to be doing that all year. So it's best to learn it now. Now I can write my numbers on the number line. So I'm going to change colors. If you can't change colors, then what I'm going to do is also put my dot. So like if I put a dot right here for my first number, I'm going to write that number above the number line so that now I can clearly see the scale, I can see my dot, and I can see what I plotted. I need to see the dot, I need to see the number. If you give me a dot but no number, it's going to be wrong. If you give me a number but no dot, it's going to be wrong. So give me the dot and the number. All right, where do I put -2/3? And be specific because I'm going to be very picky about this. Where's -2/3 go? Close to -1. So right here. No? Why not? Oh, so it has to be on this side, so I'm going to put it right there. Too close. So tell me how to put -2/3 on the number line then. Huh? Nice, I love it. Split it into thirds. We're dealing with thirds here, so let's split this segment right here into thirds. This is exactly what I was looking for, actually. Thank you. Usually it takes about 5 minutes longer, but you're on the ball, so thanks. We want to split this thing into thirds. We want 3 equal segments, okay? So try to split it into thirds. Maybe that's a third and that's a third. Does that look like I split it into 3 equal segments? Pretty close, right? So I would like you guys to do that on your number line. And now it should be pretty clear where -2/3 goes. Where does it go? On the little dash that we drew closest to -1. That's right. So I'm going to put a nice dot right here, and then I'm going to label it -2/3. Perfect. All right, my next number, where do I put that one? On the first dash that I drew. Look at that. We drew those dashes on there, and now we didn't have to think for the second one. Negative 1/3. Perfect. Next. All right, 4/3 is actually 1 and 1/3. So that means we need to be between what two numbers? 1 and 2. And since we're dealing with 1 and 1/3, split this segment into thirds again. So maybe right there and right there. That looks pretty good. And I'm going to put that dot where? On the first dash, the one closer to the 1, right here. And I'm going to label it what? 4/3. They gave me 4/3. I'm going to label it what they gave me, 4/3, even though we called it 1 and 1/3. And how about 6/3? Where does that one go? 6/3 reduces down to 2. So I'm going to put my dot right here on the 2, but I'm going to label it 6/3. Even though it is exactly 2. Label it what they gave you. Make sense? Okay, this is how I want these types of problems done. Let me switch colors here, and we'll go on to the second one. What does that say if you were to read it? X is greater than negative 2. So again, I have to draw a number line. On these types of problems, you can put that negative 2 right in the center. Give me something on either side, though. What's going to be on the left? Sure, negative 3. And then on the right? Negative 1. Perfect. That shows me that you understand that portion of the number line. Does it have to be negative 3? No, it could be negative 10. On the right, it could be positive 10. Just make sure you understand what those numbers are doing. Okay, now I have this symbol right here, and I need to represent that symbol on my number line somehow. You better remember how to do that. Very good. It is an open circle. Right on the negative 2. It's either going to be an open circle or a closed circle. Open dot, closed dot. One represents one thing, one represents the other thing. In this case, with just greater than, we need the open circle. What would you see over here to tell me that I need a closed circle? Greater than or equal to. If I can be equal to, then I have to show that I can be that exact number right there. If not, then I have to show that I can't be that exact number right there. And we represent that with that open circle. Now, what do we do from here? There's more. Yeah. So if I have this number line right here, and I have my negative 2, and I have my open circle, in the back of the book, because they can do this, and it's easy for them to do, they would shade the number line which way? It says greater than, and greater than is the numbers that are bigger than negative 2, and those numbers are to the right. In the back of the book, they'll shade the number line. That is not what I want you to do. Yes, draw a little line up, and then draw an arrow over in the direction of your shading, and that's all you got to do. I want you to do that for two reasons. One, it's cleaner. Two, it's easier. So do it that way, and we'll all understand what that means. And in the back of the book, when you look at your answers and you see that, you'll know that this is the same as this. All right, talk me through the third one then. B is something. What does that say? B is less than or equal to 4.5. Good. So what do I do? What goes in the middle? 4.5 is fine. With these types of problems, you can put that number right in the middle. That's fine. Now what? What am I putting on the right? 5? Sure. And what should go on the left? 4? Okay. And now what? Why is it closed? Because it says less than or equal to. So this one's closed. And which way am I going? Up and left, because this time it's less than. And the numbers that are less than 4.5 are to the left. I have to see the dot. I have to see whether it's open or closed. I have to see the arrow. If you don't give me a dot, it's wrong. If you don't give me an arrow, it's wrong. If you don't give me either, it's wrong. And I'll be unhappy. Give me an apple, I may eat it. But that doesn't help you with your dots. All right, I'd like you to do this last one right here. It's not as difficult as the first one, but I want to make sure you understand these, so go ahead. All right, let's go over the last one. I'm going to put my number line on here. Help me out. On the left. Okay, -3. Is it okay if somebody put -4 or -5? Is that okay? Yeah. How about on the right side? +1. Okay. +1, +2, whatever. As long as you're catching all of those numbers that you have to graph, it's good. Okay? All right, what should I do now? Equal segments, right? Fill in the rest of the integers in between. So we got -3, we got -2, -1, 0. So -2, -1, 0. Label them. All right, maybe they're not quite equal segments. We'll live. Now what? Okay, start labeling them. So this first one, -3, where's that one go? All right, so what am I going to do? I already got a -3 sitting there. I need a dot and put -3 above it. Now what? Okay, -2, where do I put that? I got to put a dot on it, and then I'm going to put a -2 above it. Now what? The +1/2, right? It's a +1/2. Where's that go? Between the 0 and the +1, so right there. Right in the middle. 1/2 is directly between 0 and 1, which is right there. So I'm going to put my dot right there, and then I'm going to say 1/2. And finally, my last one, 1, which goes, but I already have that 1 there, so I'm done. I got to put a dot. And above it, I'm going to label it 1. All right? That's how you have to do these. When I look and I see that, I'm going to get a smile on my face. When I look and I don't see that, bad things are going to happen. All right, last thing for this section, graphing and ordering real numbers. So we're doing exactly the same thing, except now the problem looks a little different. It says, what is the order from least to greatest? Graph using a number line. So by graphing it using a number line, we're actually going to put them in order from least to greatest. So that makes it kind of easy. All right. So we want to graph using a number line. Draw on the number line. Do we know what the square root of 4 is? It's 2. It's exactly 2. So I'm going to put a 2 right there just so I remember that. Do we know what 0.4 is? Could we graph that? Yeah, we could. Do we know what -2/3 is? Could we graph that? Yes, we could. How about -1.5? Could we graph that? Yeah, so we're able to graph all these now. What is the farthest number to the left that I have to have? -2 is good. And the farthest number to the right? 2. Fine. Fill in the rest of the integers. So we have -1, 0, 1, 2. -1, 0, 1. Now we're ready to graph them. So again, it's just like before, except now we have some weird numbers going on. So that first one, 2, actually the square root of 4. Where do I put it? So on the 2, I put a dot, and then I'm going to label it what? The square root of 4. The number they gave me was the square root of 4. So that's what I'm labeling it. How about the next one, 0.4? Where does that go? A little before 0, right here. A little after 0, right there. A little before half of 0. Because 0.5 would be halfway. 0.4 is closer to that than it is to 0. So I'm going to try to count out 0.1, 0.2, 0.3, 0.4. Here's 0.5. Here's 0.4. I'm putting my dot there. I'm going to show that I know that it is slightly less than half. And then I'm going to label it 0.4. Okay, next, negative 2/3. We've actually done this one before. How did we do that? Where? In between -1 and 0. We split the segment into thirds, and we're going to put that dot, the one closest to the -1, right there. Negative 2/3 there. Okay, negative 1.5. Where's that one go? Real quick. Between -1 and -2, right there, and we label it negative 1.5. And now these numbers are in order, and the problem's over. So you are able to now do the homework.